Welcome to Introductory Chemistry with Dr. H. This is a video about limiting reactants. What I'm going to talk about is what a limiting reactant is, and then how to determine a limiting reactant using a BCA table, and then we're going to talk about how to use a BCA table to find the quantities of the excess reagent at the end, how much of it remains, and what the amount of products are at the end of a process that has a limiting reagent. So this reaction, aluminum hydroxide reacts with hydrochloric acid to form aluminum chloride in water, is a common reaction for antacids. We have hydrochloric acid in our stomach, and if there's too much hydrochloric acid, say after we've had a big meal, we can get a stomach upset. Many antacids have aluminum hydroxide in them. That aluminum hydroxide will react with the hydrochloric acid and form aluminum chloride, which dissolves in the stomach and doesn't cause any harm, makes our stomach feel better, and we produce water, which is, of course, no harm to our stomach either. So this is the chemical reaction that takes place. You'll notice in this process, 1 mole of aluminum hydroxide needs to react with 3 moles of hydrochloric acid to form 1 mole of aluminum chloride and 3 moles of water. So for every 1 mole of aluminum hydroxide, we can consume 3 moles of hydrochloric acid. I'm using this word mole all the time because that's what these stoichiometric coefficients mean. Those are the mole ratios of the reagents and the products in this chemical process. So we can't talk about grams of the reagents going in. We need to talk about the number of moles of reagents that are going in and the number of moles of products that come out. In this example, I've already converted some quantity in grams of starting material into moles just to simplify this example. We're going to do another example in a minute where we show how to move from grams to moles, do the BCA table and do our analysis, and then move back to grams at the end. So say, for example, we had 0.4 moles of aluminum hydroxide and 0.6 moles of hydrochloric acid in our stomach that we wanted to neutralize. Let's figure out what the limiting reactant is, or another way of thinking about it is which reaction is going to be left over at the end. That would be the excess reactant. We know that for every 1 mole of aluminum hydroxide, we can consume 3 moles of hydrochloric acid. So if we have 0.4 moles of aluminum hydroxide, 3 times that amount would be 1.2 moles of hydrochloric acid. So we can see right away that we don't have enough hydrochloric acid to react with all of that aluminum hydroxide. So this reagent, the hydrochloric acid, we don't have enough of it. So what we're going to call this is our limiting. That's our limiting reagent, and this is going to be our excess reagent. So we've now identified our limiting reagent using the coefficients, the stoichiometric coefficients in front of those two chemicals in our starting materials, right? The starting materials, or the reactants, are the ones that are going into the reaction. The next thing we need to do is we need to go ahead and fill out our BCA table, but it's really important that we start with our limiting reactant because that's what's going to control how much can be consumed in the reaction. So let's do that. So the first thing I did here in this table was I said, well, I know that this amount of moles of hydrochloric acid, that's going to limit our process. So all of that hydrochloric acid is going to be consumed. So the change in the amount of hydrochloric acid is going to be minus 0.60 moles. And at the end of the process, afterwards, we have 0 moles of hydrochloric acid left. Now, in order to find the amount of aluminum hydroxide that's consumed, I use a ratio, and this ratio comes right from those stoichiometric coefficients. So for every 1 mole of aluminum hydroxide in the reaction, I need 3 moles of hydrochloric acid. And what I know is that 0.6 moles of hydrochloric acid reacted. So my question is, how many moles of aluminum hydroxide does that consume? And when I did that math, I found that that was 0.2 moles of aluminum hydroxide. So that's how much of the aluminum hydroxide is going to react. And if I subtract 0.2 moles from 0.4 moles, I see that after the reaction I have 0.2 moles remaining. That's how much remains at the end in moles of that particular reagent. So the first thing is we had a balanced chemical equation. Then we put the moles of the reagents into the BCA table. We determined the limiting reagent, and now we're working on completing this BCA table. And the key thing is that I want to remind you is you need to start with the limiting reactant and then use the mole ratios in the reaction equation to figure out all of the other parts of the BCA table. So now we figured out the reactant side. Let's move on and talk about what happens in the products. What you'll notice is the coefficient on aluminum hydroxide is the same as the coefficient on aluminum chloride. This is a reactant, so it's going to be consumed, so there's a minus sign in front of that one, but this is a product, so it's going to be formed. So if it has the same stoichiometric coefficient, the same number of moles is going to be consumed or produced. So aluminum chloride, the change in the amount of aluminum chloride is going to be plus 0.02 moles of aluminum chloride. You can do that math using the mole ratio just the same, right? So I'm just pointing out that you don't have to do the math again, but I've done the math at the bottom so you can see how you would find the number of moles of aluminum chloride that's consumed. And because it's being formed, that's how much remains at the end, 0.2 moles of aluminum chloride. The same process applies with the water. And again, what I've done is I sort of notice here that there are 3 moles of HCl consumed and 3 moles of water produced. So I know to expect that if we lose 0.6 moles of hydrochloric acid, we're going to gain 0.6 moles of water. We can, of course, use the mole ratios, 3 moles of water to 3 moles of hydrochloric acid, to sort of prove that. So if we have 0.6 moles of hydrochloric acid consumed in the process, when we solve for x, we can see that these two cancel to become 1. It's got to be 0.6 moles of water at the end. So now we have our complete BCA table. And now we can really see why HCl is called the limiting reagent, because at the end of the process, we still have 0.2 moles of aluminum hydroxide. All of the hydrochloric acid is gone. We formed 0.2 moles of aluminum chloride, and we formed 0.6 moles of the water. So that's the complete BCA table. Let's do another example that illustrates how to sort of do this problem as you would normally do it. Usually what we're doing is we're starting with grams, something that we can measure. We know that we can't work directly with grams because they don't correspond to those stoichiometric coefficients in a reaction, so we're going to convert first to moles. So let's take a look at this example. This is another example that relates to stomach problems after you eat too much. So Alka-Seltzer uses this reaction to create those bubbles. When you drop Alka-Seltzer into water, the bubbles that come out are these CO2 bubbles. So the reaction that's going on in the Alka-Seltzer tablet is sodium bicarbonate is reacting with citric acid that's inside the Alka-Seltzer tablet to form carbon dioxide, a little bit of water, and sodium citrate. So that's the way we would describe in words that chemical reaction. And again, I want you to notice that there's stoichiometric coefficients here. So 3 equivalents, or 3 moles of sodium bicarbonate, are going to react with 1 mole of citric acid to form 3 moles of carbon dioxide, 3 moles of water, and 1 mole of sodium citrate. All right, so let's just sort of begin our process again. This reaction has already been balanced, but you would need to check to make sure the reaction is balanced at the beginning, because these stoichiometric coefficients are the ones that are determined when you balance the chemical equation, and those are the ones that ultimately govern what the limiting reactant is. And then we're going to convert those things into moles. So the first thing I did, and I've sort of illustrated the math down here, is I have 1 gram of sodium bicarbonate and 1 gram of citric acid. So I need to do a gram-mole conversion using the molecular weights. And so what I found is I have 0.0119 moles of sodium bicarbonate, and what I see is that I have 0.0052 moles of citric acid. Great. Now let's think about what our limiting reactant is. So I know that I need 3 times as much of the citric acid in order to react with the sodium bicarbonate. If I multiply the amount of citric acid here, 0.0052, by 3, what I see is I have, that number is greater than the moles of sodium bicarbonate that are there. So there's not enough sodium bicarbonate to react with all of that citric acid. So I'm going to go ahead and mark this as the limiting reactant, and this one's going to be the excess reactant. And then we're going to go ahead and start filling in our BCA table. So sodium bicarbonate is our limiting reactant, so we're going to do that column first. So we know that in this process, all of that sodium bicarbonate is going to be consumed, and so we'll have no sodium bicarbonate at the end after the reaction. And then we can use a mole ratio, just like we described before, to find the number of moles of citric acid that are going to be consumed. So for every 3 moles of sodium bicarbonate, 1 mole of citric acid is consumed. And so what the actual number of moles of bicarbonate we have is 0.0119 moles of sodium bicarbonate. And so we can solve for this x. When I did that process, I found that that x is 0.00397 moles. That's the number of moles that are going to be consumed. So I put a minus sign there, and that's in the change category. That's how much is going to change. And so then if I wanted to figure out how much citric acid was left at the end of the reaction, I just simply did this subtraction, and I found that 0.0052 minus that amount of moles is 0.00123 moles of citric acid remain at the end of this process. Great. Let's keep filling out our BCA table. Now what we're going to do is use the mole rate, stoichiometric coefficients in the products to figure out the number of moles and their change. At the beginning of these chemical processes, we assume that there are no moles of any of the products. So we have no moles of CO2, no moles of water, and 0 moles of sodium citrate. We can see, we can use the ratios, or we can just notice that the stoichiometric coefficients of sodium bicarb is the same as CO2, I know that this is a product, so it's a positive sign because it's being formed, while this is a reactant, but the number should be the same, so 0.0019 of CO2, moles of CO2 is consumed. That's how much that will remain at the end. Same with water. The stoichiometric coefficient is 3, so 0.0019 moles of water will be formed, and that's what will remain at the end of the process. I noticed that the stoichiometric coefficient in front of sodium citrate is the same as the stoichiometric coefficient in front of citric acid, and so the number will be the same, but the sign will be different. So 0.00937 moles of citric acid will be consumed, but the amount of sodium citrate that will be formed will be 0.00397. And here, instead of doing a subtraction, this is the amount that actually remains at the end of the process, right? So we have 0.00397 moles of sodium citrate at the end. All right, so now we've completed our BCA table, and now we can really see what remains at the end of the process. If we actually were in the lab and we wanted to do a measurement or something like that, we would actually be measuring grams of things. And so now what we need to do, and I've sort of added to step 5 here, is we need to find the number of grams. Well, if we have the number of moles of things, we can easily find the molecular weight of those things and convert that into grams. So here I've just done a quick example of that process. And what you can see is if you take the number of moles of citric acid that remain times its molecular weight, you find 0.236 grams of citric acid remain. That number is less than 1, so that's good because we knew we consumed some and we started with 1 gram. So that's just, a brief check. We do the same with the products. Here's an example of doing CO2. 0.52 grams of CO2 are formed. That's the number of grams of CO2 and 0.019 moles of CO2. If we keep going, and we can do that for the water, and we can also do that for the sodium citrate. And now we've got sort of a complete analysis of what happens in this reaction. We expect to see none of the sodium bicarb left. We've got 0.236 grams of citric acid. That's the starting material that remains, so we call that one the excess one. 0.524 grams of CO2, 0.214 grams of water, 1.02 grams of sodium citrate. And after you've done a process like this, there are lots of calculations, lots of chances to make little mistakes. It's always a good idea to check your work. And one thing we know is that in a chemical reaction, what's happening is the atoms aren't being created or destroyed. The atoms are just changing positions and changing partners. And so what that means is the total mass of the stuff that remains after a process should be equal to the total mass that we started with. And in this reaction, we started with a total of 2 grams, right? We had 1 gram of bicarb, 1 gram of citric acid. And so what that means is if we sum up the weights of all the products and the remaining reactant, we ought to get 2 grams. And so if you do that, what you see is that those things sum within significant digits to 2 grams, which means we didn't make any mistakes along the way. Well, I hope you found this video about limiting reactant useful. I highly recommend using a BCA table to help keep track of all the amounts during a chemical process. It's a lot easier than the method that's shown in your textbook, I think. So hope you found this video useful.